Okay, so we have seen what a low pass filter looks like both in the time domain and in the frequency domain. Now, let us extend this topic a little more, and here again we are going to leverage our equivalence that we have seen, or the duality that we have seen between multiplication and convolution, and specifically between the rectangular pulse and the sinc function. So the low pass filter that we had we have seen just now, it is called an ideal low pass filter. And whenever we put the word ideal as a prefix in front of any operation, you have to think of that as being too perfect, meaning that in practice it may not be achievable. And that is indeed the case. This impulse response, which is the sinc function, is not actually practically realizable. There are actually two problems with it. One is that its length is infinity. The sinc function is sine x over x. Sine function uh, is defined from minus infinity to plus infinity of time, or this value n, index n. So it is infinite in length. But on the other hand, the good thing is that because of the divide by x, the sine function keeps on decaying, and as n becomes bigger and bigger, the absolute value of n, as it keeps on becoming bigger and bigger, the value of the sinc function keeps on decaying. That is seen here. At n value of about 20, you can see that sine sinc function has decayed quite a lot. So maybe this is not that big of a problem, although the sinc function is infinite in length. Maybe we can just ignore some samples that are known to be quite close to zero. How do we ignore some samples of sinc which are close to zero? Well, all we do is we multiply the ideal impulse response h of n with a window, a gate in the time domain. This is now multiplication in time domain. The width of this gate is capital N samples. Now we want to make capital N to be sufficiently large. On this slide, for example, if I make capital N to be maybe only 10 samples, then that is not sufficiently large, because then this rectangular window will zero out all of these samples which are not actually very small. Even if I make capital N to be 20, then we can see there is still a lot of energy outside of plus minus 10. But maybe if I make capital N to be 100, then maybe fine. I mean, then the sinc function would have dropped to a sufficiently low level. And then if I zero out all of the other samples that are outside of this rectangular window in time domain of width and samples, maybe it is not a big deal. So maybe this h capital T of n is something that is practically realizable because it has only capital N non-zero samples. And so that those n samples can be stored, for example, in the computer memory. The question is that this is the ideal filter, the sinc function, and it is the ideal filter which has this nice rectangular window which I want in the frequency domain. The practical filter is this h capital T of n, or h capital N of n. But that is not exactly sinc function. For most of the part, it is exactly same as sinc function, but then some of the values of sinc which are pretty close to zero, that we are just ignoring them by multiplication with this gate in the time domain. So what we will get is not exactly sinc function in time domain. And so what we should expect is that even in the frequency domain, we won't get this nice rectangular pulse anymore. The question is what we will get instead. Well, again we go back to the duality between multiplication and convolution. Here we are multiplying in time domain. So in frequency domain, we are convolving the Fourier transform of this with the Fourier transform of the rectangular gate. But we know Fourier transform of this sinc function. We know that is this ideal low pass filter. It is this nice rectangular pulse. But now we are convolving that rectangular pulse with the Fourier transform of this rectangular window in the time domain. What is the Fourier transform of this? It is the sinc function. So here we are kind of going back and forth between sinc and rectangular pulses. And so in the frequency domain, the practically realizable filter will be a convolution of the ideal rectangular pulse in the frequency domain, except there will be a convolution with this sinc function in the frequency domain. And because of this convolution, there will be some ripples uh, that we are now going to look at. And these ripples are going to be always there. As we make this capital N bigger and bigger, uh, the ripples will become finer and finer. They will become thinner and thinner. But the height of the ripple will not reduce, unfortunately. That is known as Gibbs phenomenon. So let us look at it. Okay, so this is my H capital T of N for capital N equal to 10. I am having only 10 samples. See this signal here, I am just keeping 10 samples of this signal. And so you can see on the left hand side, it doesn't look at all like a sync. It probably looks like a triangular pulse now. In frequency domain, I took this red colored ideal filter response, the rectangular pulse, but now I had to convolve it with a sinc function in the frequency domain, which is the Fourier transform of this rectangular pulse of the frequency domain. But because capital N is pretty small, it is only 10 samples, in the frequency domain, this sinc is pretty wide because again of the duality reason. And because that sinc function is pretty wide, you see pretty wide blobs. And also this vertical edge got spread out quite a lot. And so instead of rectangular pulse, you got this blue part, which is what is actually realized, capital HT of F. What happens if I make capital N to be 20? Now in time domain, I allowed some two ripples outside of the main ripple to be included. Basically, I made capital N bigger in the frequency domain, therefore this sinc function will become thinner. And so indeed, these ripples that I am seeing in the frequency domain are smaller, and this blue line becomes slightly more parallel to the ideal vertical red line. And these ripples became kind of thinner even in this main part. When n is equal to 40, now my pulse is starting to look quite a lot like a sinc function. And therefore, in the frequency domain, what I'm getting is something that looks quite a lot like this rectangular pulse. Although still there are many ripples. But those ripples have become definitely more thinner. Again, that is happening because this capital N is becoming bigger. The width of this time domain gate is becoming wider. And therefore the sinc function in frequency domain, the Fourier transform of this rectangular pulse, is becoming thinner. And that is why these ripples that you are seeing that are coming from this sinc function, convolution of this red rectangular pulse with the sinc function, those ripples are becoming thinner as well. So as I keep on playing this example, making n bigger and bigger, you see that I'm getting a shape which looks now a lot like the ideal rectangular shape, except the ripples are refusing to go away. And what you will see is that the relative height of the ripples is remaining about same with 100 samples, with 500 samples. Also, now it looks almost like the rectangular pulse that I wanted, except the height of the ripple is refusing to die down. The ripples themselves become very thin now, and overall shape does look a lot like the rectangular ideal shape, but there'll be still this Gibbs phenomenon happening at the edges. Okay, so we will stop this video here, and then we'll come back for possibly the last video of this topic.